Hello, classmates. Methods of analyzing DC circuit are various. We have studied resistance connection and equivalent transformation of power supply earlier. Next, we will learn a new analytical method, Kirchhoff's law. Kirchhoff's law include Kirchhoff's current law and Kirchhoff's voltage law. Let's first get to know the Kirchhoff's current law, which is used to describe the circuit, voltage, and the current of each part. Including Kirchhoff's current law and Kirchhoff's voltage law. Before discussing Kirchhoff's law, let's first define several circuit-related terms. Branch circuit, one or several two-terminal elements that are connected in series without branching form a branch circuit. On the same branch circuit, the current passing through each element is the same. A branch circuit with a power supply is called an active branch circuit, while a branch circuit without a power supply is called a passive branch circuit. Node. A connection point of a branch circuit with three or more articles is called a node. Loop. Any closed path in a circuit is called a loop. Mesh. A loop with cross-connected branch circuits inside is called a mesh. In the circuit shown in the figure, point A and point B are two nodes. There are three branches in this circuit. There are three circuits, number 1, number 2, and number 3. There are two meshes in number 1 and number 2. After learning related terms, let's practice. For example, in the circuit shown in the following figure, how many branches, nodes, circuits, and meshes are there? Referring to the definition, in the circuit diagram, we can sequentially identify that there are 6 branches, there are 4 nodes, and a total of 7 circuits. We also discover 3 meshes. In fact, if there are a certain number of meshes, there will be the same number of meshes. And the number of independent nodes in the circuit is equal to n minus 1. Number of independent circuits equals to the number of meshes. Kirchhoff's current law is KCL for short, states that at any moment, the algebraic sum of currents flowing into any node is always equal to 0. This can be mathematically expressed as sigma I equals 0, where I represents the current of an arbitrary waveform, or the current in a DC circuit. In the given part of the circuit shown in the figure, if we consider the current pointing towards the node as positive and the current moving away from the node as negative, we can apply KCL to node A and write the equation as negative I1 plus I2 minus I3 minus I4 equals 0. For example, to find the current I1, I2 in the circuit shown on the left, first of all, we should observe that only the magnitude and direction of the current are known in this circuit. Therefore, we give priority to using Kirchhoff's current law to solve the problem. There are 2 nodes in this circuit, and we can use KCL once on the left node. The equation is negative 4 plus 7 plus I1 equals 0, and we calculate that I1 equals negative 3a. Next, we can use KCL again at the right node. The equation is negative I1 minus I2 plus 10 plus negative 12 equals 0, and we calculate that I2 equals 1a. As I1 has a negative value, it shows that its actual direction is contrary to the reference direction. To take another example, analysis of the relationship of current I1, I2, I3, I4 in the figure below with KCL. According to Kirchhoff's current law, we can establish the KCL equation, I1 minus I2 plus I3 minus I4 equals 0. This equation can be transformed into another form, I1 plus I3 equals I2 plus I4. At this time, another form of KCL can be obtained, i.e. for this node, the total current flow into this node and the total current flowing out of the node is equal. KCL is not only suitable for nodes, but also applicable to closed surfaces that surround multiple nodes. As shown in the lower left picture, enclosed closed surface can be treated as a generalized mode, also known as supernode. Consequently, the total current flowing into this node is equal to the total current flowing out of the node, that is, I1 plus I2 equals I3. Similarly, in the picture on the right, if we need to determine the value of I, it is challenging to analyze using conventional methods. However, if we consider the entire right side as a closed surface, treating it as a generalized node, total current flowing into this node is equal to the total current flowing out of the node. In this case, there is only one current flowing into the node and no current flowing out, resulting in an outflow current of 0. So I equals 0. For example, a transistor has 3 electrodes, and the direction of each pole is shown in the figure below. What is the current relationship between poles? Although we haven't studied crystal triodide yet, we can regard transistors as a closed surface, where IE equals IB plus IC. In conclusion, we know that Kirchhoff's current law, KCL, points out that in the circuit, at any moment, the algebraic sum of all branch currents for any node is always equal to 0. As for more knowledge, see you next time.